Hello everybody, my name is Antreas I'm with the University of Cyprus, and in this presentation I'm going to talk about the paper titled Exploring Model Inversion Attacks in the Black Box Setting. This is a joint work between University of Cyprus and Science Center of Excellence. So let's get right to the point. Despite being so popular, machine learning or ML models have been proven vulnerable to various security and privacy attacks, such as membership inference, adversarial samples, and model inversion. In this paper, we focus on model inversion attacks that aim to generate inputs that resemble the original ones used for training an ML model. Such information leaks may enable the de-anonymization of users and expose personal or sensitive information. In order to understand how these attacks work, let's give an example for the first black box ML attack proposed by Friction back in 2014. Assume that we have a target model MT, which is a function f that takes as input a feature vector x1 to xn with n dimensions, and outputs a prediction y. Now, the attack of Friction et al. Uses black box access to f in order to infer a sensitive feature, in this case x1, given some knowledge about the other non-sensitive features, x2 to xn, the output of the target model y, and any other auxiliary information regarding the target model. What they essentially do is that they pick the value for x1 that maximizes the confidence score for the winning class in y. Model inversion attacks can be conducted under specific settings and assumptions, and as a result experience different limitations. For example, we have a number of white box MI attacks that assume access to the target model's internals. We also have MI attacks that target only low complexity MI models. And we also have attacks such as the one proposed by Friction et al. That only infer a small number of sensitive features from tractably and often discrete domains. As a matter of fact, only a few black box MI attacks, which are fully agnostic about the target model's internals, have been proposed in the literature. And even these attacks often suffer from significant limitations that affect both their effectiveness and their efficiency. For example, some of them generate semantically meaningless reconstructions that do not resemble, which are not recognizable as they are granted, and others just take too long to complete. As a result of this paper, we present a feasibility study for black box model inversion attacks on image recognition models, and we consider this work as a feasibility study for two reasons. First, model inversion has a probabilistic nature in contrast to other attacks in the field which have clear baselines, for example, membership inference. And second, existing black box MI frameworks do not perform well in terms of either effectiveness or efficiency, or in many cases, both. So how do we tackle black box model inversion? The first approach is to start from random pixels and continually perturb them until the confidence score of the winning class is maximized. Now, this has the advantage of being simple and generative. However, this approach is known to generate full-link images, which are images that yield the target class with high confidence, but are irrelevant to the background, are visually irrelevant to the background truth. And also, this approach requires a huge amount of iterations for reconstructing a single sample, let alone a complete dataset. A second approach, which was first proposed by Yang et al., is to leverage a public dataset that is descriptively similar to the target model's dataset. This dataset may share basic descriptive characteristics and by assumption distribution to the target model's dataset, but does not contain the same training and testing instances. For finding such a dataset, one can probe the target model to obtain basic descriptive information, for example, the task context, the image's resolution, etc., to find and download a similar dataset. For example, one can use AT&T database of faces, celebrate your Ferret, for targeting any face recognition model. Now, the advantage of this approach lies in the assumption that the images containing both sets share features which would make some of the images of the public set likely to maximize the confidence score of a certain class of the target model. However, the way that Wang et al. Framework works has the following four shortcomings. First, their method only reconstructs images which are the average of all the auxiliary samples that yield a specific target class with a certain confidence score. Second, the number of queries made to the target model equals to the size of the descriptively similar dataset. Third, there is no any search for the inversion model's latent space for generating more representative for each target class reconstructions. And finally, their method only returns one solution per target class. So in this paper, we propose DPMI, and now let's see how DPMI works in practice. DPMI actually exploits the benefits of the two aforementioned approaches. First, it trains a generative model on the descriptively similar dataset, which allows us to learn the structure of the input and by assumption features that are shared between the two sets. And second, DPMI searches the inversion model's lattice space in order to generate images that maximize the confidence score of the specific target class. What it essentially does is that it modifies the coding given as input to the decoder for constructing an image that maximizes the respective confidence score. But how does DPMI actually tackles Wang-et-al's limitations? First, in our setting, we do not reconstruct average samples. DPMI adopts the classic training paradigm for autoencoders and encodes and then decodes each auxiliary sample such that it minimizes the respective reconstruction loss. Second, DPMI decouples the number of queries made to the target model with the size of the descriptive image in Antreas. In DPMI's context, the number of queries is explicitly controlled by the black box optimizer. Third, DPMI by design supports several black box optimizers for exploring the inversion model's lattice space and generate more representative reconstructions for each target class. And finally, depending on the utilized black box optimizer, DPMI can return more than one solution per target class. Now, DPMI is modular, meaning that any adversary can plug their own black box optimizers for searching the inversion model's lattice space. And actually, one can even replace the inversion model, which in our case is a convolution variation autoencoder or SVI, with other generative models such as GANs. Now, DPMI currently supports 6 black box optimizers. The first 4 optimizers are referred to as single class because they can only target one class per evocation and they can only return one solution. And the last 2 optimizers can target all classes at once. MapElites can return one solution per target class, while CVT MapElites can return k solutions per target class. Now, there is no any scientific consensus when an MI framework is considered effective or not. As a result, in order to effectively conclude about our framework's performance, we utilize all the approaches found in the literature. Specifically, we show actual reconstructions along with the ground truth. We also use the relevant quantitative metrics. And finally, we conduct user studies with human participants. Before presenting our results, we must say that model inversion comes in 2 flavors. The first is data reconstruction, where the adversary aims to reconstruct the sample given its yielded confidence score vector on it. So it has the confidence score vector from the target model and aims to reconstruct the sample. And the second setting is training class inference, where the adversary aims to reconstruct a meaningful sample for each target class by only being able to query the target model and receive the confidence score vector as a response. In this paper, we focus solely on the latter setting for 2 reasons. First, Wang-et-al reconstructs samples with low recognizability in this setting. And second, having the confidence score of the target to be inferred sample is a rather strong assumption. Now let's deploy DPMI on a target of modest difficulty but with low actual privacy implications for showcasing its mechanics. In particular, we deploy DPMI for inverting hundreds and digit recognition model. So we train the target model, which is a CNN on IMNIST, and we will train the inversion model on IMNIST letters. As you can see, in this image, DPMI reconstructs images which are highly identifiable as their ground truth. Again, this graph shows the performance of our framework for each black box optimizer. You can see that all of them perform comparably well. MapElites and CVT MapElites achieve the best performance. We also present the efficiency results for our framework. For this setting, we can see that DPMI is actually highly efficient, managing to reconstruct samples in only 1.29 seconds for single class attacks and 4.5 minutes for all class attacks. Now let's deploy DPMI on a target of higher complexity, which is a phase recognition model. In this setting, we train the target model, which is a CNN on ATT database of phases, and the inversion model on cell-based dataset. Now this figure shows a comparison of DPMI's reconstructions with white box MI frameworks proposed by Fredrickson et al. As you can see, DPMI manages to reconstruct comparable images with the ones achieved for the white box adversaries. In this figure, we compare DPMI with Wang-et-al, which is directly comparable since both frameworks operate in black box setting. As we can see, DPMI manages to reconstruct recognizable images with recognizable characteristics, whereas Wang-et-al's framework reconstructs only average images that only preserve general features of the faces, such as mouth, nose, and eyes. Also, you can see that the confidence scores derived when feeding us input our reconstructions are very close and in many cases identical to those observed when feeding us input the ground truth images. Again, this graph shows the performance of our framework compared to other attacks for all black box optimizers. Although the results are clearly lower, they still designate significant privacy violation. Here we compare our approach with Friction's white box MI framework. We can see that DPMI achieves comparable performance with white box MI attacks. And here we also compare DPMI with Wang et al., which are both black box MI frameworks, use irrelevant quantitative metrics. In most cases, we can see that DPMI outperforms state of the art. Now we can see the efficiency here. Again, the results are designate that DPMI is highly efficient, managed to reconstruct faces in acceptable times, let's say. So what have we seen in this presentation? We have seen a feasibility study for the effectiveness and efficiency of black box MI attacks on CNNs used for image recognition. We introduced DPMI, which is a modular MI framework that supports several black box optimizers. And finally, we saw that optimizers returning multiple diverse solutions for each target class, such as CVT abilities, are the most effective ones for tackling model inversion. Thank you very much.
Are there any questions? Okay, just a second.
Hello, thank you for your presentation. Did you consider using other generative models and maybe like some GAN, like style GAN, which perform well on faces and has good disentanglement of the latent space, which may make the optimization process easier?
Actually, we utilized, in our case, so the question is why we actually utilize convolutional variation autocorrelation and not GANs. This is, okay. We choose to go for the simpler approach, let's say, although not the best performing in the state of the art, since we had previous experience in the lab using that specific model, but we are currently working on using GANs, to be honest, for incorporating them into DPMI and compare and report their performance in real-world settings. Our preliminary results suggest that the performance is higher, it's dramatically higher, to be honest, because GANs can generate images with more, let's say, subtle differences and more detail. So yes, we are currently exploring this aspect, and our results suggest that indeed they perform better compared to CVIs.
Okay, let's quickly do one question from online. Does tuning the generative model affect the overall MI performance?
Indeed, tuning the generative model indeed affects to some extent the MI performance. However, what is important in our approach is how the different components interplay. For example, the black box optimizer with the utilized generative model and not the actual generative model per se. However, yes, as I've said earlier, it indeed affects to some extent the MI performance, yes.
Okay, let's thank our speaker again. And please approach him during the break.